Alright guys, so I wanted to do another type of problem where this problem is really common on your AP test on both the multiple choice as well as a possible free response question, and that is one of these maximum projectile range problems. And in a lot of these questions, they don't want you to use numbers, they actually just want you to show how something works in terms of variables. So this says, in order to calculate the maximum range of a rocket, you fire the rocket straight up, and then you record the time it takes for it to return back to the ground. And we're going to call that specific time t trajectory. So it says, based on this single piece of data, based on this t trajectory, that's what we're revolving time around, we want to know on part A, what is the speed with which the rocket is launched? Okay, so speed with which rocket was launched, that's my goal to figure out for A. So that means I'm trying to find some type of initial velocity, but there is a key phrase in this problem that tells me a lot more, and that is that we fired the rocket straight up. So if I'm firing the rocket only in the vertical direction, I don't have to worry about any type of horizontal velocity. So I'm only worrying about a velocity in the y direction. So I want to know my velocity, my initial velocity in the y direction. That's what I'm trying to solve for here. This is my goal. And I have, I want to draw two. We're launching a rocket. And I know that I initially launch it with some type of initial velocity. And then when it gets up here, at the peak, it's going to be 0. So I have an equation, a kinematic equation that says Vy equals my initial y velocity minus the acceleration due to gravity times time. I know that kinematic equation. I know that at the top of its trajectory, I've only gone halfway through the trajectory, but at the top of that trajectory, that velocity is 0. So Vy, I could set here to 0. And then I would say I have my initial velocity times acceleration to gravity times time. But this time isn't the trajectory time. I only went halfway through the trajectory. I only went to the peak. I want to know what the entire thing is, like when it comes back down. So I actually want to call this time peak. And let's rearrange this where we're actually going to say that the peak time equals whatever variables I have. So the peak time, if I rearrange for time, I would get then my initial velocity in the y direction over gravity. Well, if this is the time that it takes to go to the peak, then I know that I'm going to go through the exact same thing coming back down. So I found half of it, of the trajectory. If I just double this, I'll find the entire trajectory. So I know that t peak is this, so that means that t trajectory, the time that it takes for the rocket to go through its whole path, is just 2 times that initial velocity in the y direction over gravity, over acceleration due to gravity. Okay, so they want me to express things in terms of trajectory time, and my goal, though, was to show, using variables, what the initial velocity was in the y direction. Well, I have that initial velocity here in the y direction, so I can just rearrange this equation for my initial velocity in the y direction, and then I would have my answer. So if I rearrange this, I'm going to end up getting Vy, my initial velocity in the y direction is equal to the trajectory time, and that would be times g divided by 2, and that's my answer. I wanted to show what the speed was. I know it's only in the y direction, and it was the initial speed because I want to know what it was launched with. So that tells me that I also expressed it in terms of the time for the entire trajectory, which they asked me to do. So that solves A, but now I want to do B. And B says, compute the rocket's range as a function of the angle of elevation theta and the initial speed VO. So I don't want this necessarily I don't want Vx, I don't want Vy, I want to show VO, that initial speed of the vector. Okay. So I know that range is just simply how far something landed from where I originally projected the object. So we know that range would be trying to find some type of x position. And we have a kinematic equation for that. X equals that initial x velocity times time. Oh, but we said in this problem, or they asked us to in this problem, to make sure that time was the total trajectory time. Well, lucky for us, in part A, we already solved for that total trajectory time. So we said that the trajectory time was equal to 2 times the initial velocity in the y direction over g. But there's one more problem. This question says, I also have to compute the range as a function of an angle, as a function of theta. Well, that means I have the initial velocity in the y direction, and I know that there has to be some type of angle then that's associated with that since it's broken down into a component there. So that would be VYO is the same thing as saying that I have the initial velocity vector, so we're just calling that whole thing VO, times sine theta. Because in the y direction, it would be the sine theta. And that would be my original vector times then that sine theta. So this gives me my angle for the t trajectory. So I've incorporated my trajectory time and my angle, and then I've also incorporated that just initial velocity vector. I'm trying to take out the components. I just want the initial velocity vector, and then I want to also show angles. So we did that. So this is my t trajectory. So let's plug this in for t trajectory. I have x equals then my initial velocity in the x direction times 2 VO sine theta over g. Okay, well I have one more problem, and that is this velocity is in the x direction, or it's that x component, so I need to also account for it. I want to express this in terms of just the original vector, or that overall resultant vector, VO, and then also an angle. And we know that the x component would just be VO times cosine theta. And then I'm going to multiply that by, again, my t trajectory, which is VO sine theta over g. Okay, well now there's a lot of variables here. I want to try to simplify this down as much as possible to just clean it up. So let's rewrite that up here. X equals, what did we have? VO cosine theta times 2 VO sine theta over g. Okay, so let's clean this up. I can say that I have VO times VO, so I have VO squared. And then I have times 2, and then sine theta and cosine theta. And that's all over g. Now, if you remember your fantastic trig identities, then you would know that 2 sine theta cosine theta, I could write a different way, which is sine 2 theta. And to clean this up, that's exactly what I want us to do. So I have x equals VO squared times sine 2 theta over g. And that's exactly what we have for our range equation that we use when we use those kinematic equations and when we're trying to find range. So we actually just derived our range equation, and you didn't even know it. It's fantastic. Okay, now let's look at the last question. That one. It says, at what angle is the range maximized? Well, we know that for any projectile, that the maximum range is going to be 45 degrees. So this one is just simply just knowing the content. So I don't even have to do any work for part C. I just had to know that I can have my maximum angle at 45 degrees. That's going to give me my largest range. So there's another practice problem by using these variables, and I would like you guys to try this. Now, over the weekend, I will post the answer for this one on your blog. I'll actually have it scheduled to be posted on Saturday morning, so that way you can see that. Because you have, I think maybe one or possibly two practice problems where you have to do something similar to this one or what we just did. But I think it'd be good for you to practice this. So you can practice this one now in class, but you also have a worksheet that Mrs. Patel is going to pass out to you. So that worksheet is going to be due on Monday, and it's just practice problems with projectile motion. Okay? Now, if you have some problems, I kind of wrote out some little helpful hints for you here. In case you want to read those are for you. And I hope you guys have a really great weekend, and I will see you in a week. I'm so excited. Bye!